might have blinked and missed it, but we've actually started to develop a lot of valuable topology in the last few months. But there's a huge question that we've left unanswered, and that is, why? Why do we have all these properties like countability and connectedness and compactness and so on? One reason is that we're trying to build a big list of what are called topological invariants. All an invariant is something that doesn't change, doesn't vary, no matter how I might express my topological space. So, for instance, whether I give you a torus by thinking about a donut or by thinking about a square with sides identified, it's still compact. That's because compactness is a topological invariant. It doesn't change based on how we present the topological space. Or, to use better language, compactness is preserved by homeomorphism. Okay, so why do we want topological invariants? And the reason is, we want to show when two topological spaces aren't homeomorphic. That might feel a little weird, right? But the idea is, it's sort of straightforward to show when two topological spaces are homeomorphic. All you have to do is actually cook up a homeomorphism. Give me an explicit continuous map between x and y that has a continuous inverse, and ta-da, x and y are homeomorphic. But showing that two spaces are not homeomorphic, that means that there can't possibly be any homeomorphism between x and y. And how do you show the non-existence of something? That's a lot trickier to do. You can't just say, well, I couldn't find a homeomorphism, so I guess they're not homeomorphic. Because what if there is a homeomorphism, and you were just dumb and couldn't find it? I think that's what the kids call a big mood. So instead of saying x and y are not homeomorphic because I couldn't find a homeomorphism, we could instead say x and y are not homeomorphic because x has a property that y doesn't, and a homeomorphism would have preserved that property. That's a lot better. So, for instance, the torus is not homeomorphic to the plane. They're both two manifolds, but the torus is compact while the plane isn't. Compactness is a topological invariant that shows that no homeomorphism can exist between the torus and R2. There's a snag though. This strategy is only ever as good as our list of topological invariants. Say we have two spaces x and y. We can't find an explicit homeomorphism between them, and so we expect that x and y are not homeomorphic. So we go hunting for some property that x has while y doesn't. But we check every property that we know, and unfortunately, x and y always both do or do not have that property. Well, crap, now we're really stuck. For instance, let's handle a specific example. Is Rn homeomorphic to Rn minus a point? It feels like the answer should be no. And for small values of n, it's pretty easy to see this. If n equals 0, well then R0 is just a point. And certainly a point is not the same as a point minus a point, the empty space. If n equals 1, then again it's easy to see that the answer is no. R1 is the line, which is path connected. But R minus a point is not path connected, there's two pieces. But now, what if n is 2? Are the plane, and the plane with a hole in it, homeomorphic? The answer is not so obvious. I think just about every property that we've discussed so far that holds for the plane also holds for the punctured plane. Both are non-compact, second countable, path connected, connected, etc. The temporary fix to this problem is to keep cooking up new topological invariants that distinguish between your two spaces, where every other invariant thus far has failed. That's what we're going to do over the course of the next couple episodes. Of course, remember that this can only ever be a temporary fix. That's because there's always the possibility that you eventually run into two topological spaces that agree on every single one of your invariants, but aren't actually homeomorphic. So you have to just keep cooking up new topological invariants to distinguish between them. That's why tools like classification theorems or the innata lemma are so valuable to mathematics. They tell us, in no uncertain terms, here are all of the homeomorphism classes of your spaces. Here are all of the isomorphism classes of your groups. Here are all of the things that you have up to the right notion of sameness. So, let's apply our temporary fix and start to cook up a new topological invariant that should distinguish between the plane and the punctured plane. The idea is born from path connectedness. So we know that path connectedness just means that if you have any 2 points in your space, then you can connect them with a path. If we're being a little bit more thorough though, then we say that if x and y are points in your space big X, then a path is a map, P, from the interval 0, 1 to x, such that P of 0 equals x and P of 1 equals y. But, and this is a dumb thing to do right now, but S0 is 2 points. Remember that the circle S1 is all of the points which are the same distance from the center. If we go down a dimension and pick a center, then there's only 2 points that are distance r, the radius, away from that center. And just like the disk D2 is filling in the inside of the circle S1, the interval D1 is just filling in the space between the 2 points of S0. So here's another way to say what a path is. Given any map, little f, from S0 to x, there exists another map, big F, from D1 to x that extends little f. In other words, big F agrees with little f on the overlap, which is S0. This is saying the same thing. Little f is the choice of two endpoints, x and y, and big F is the path from x to y. Like I said, that's a dumb way to think about paths when we already have a much easier way. But the benefit of this new way of talking about path connectedness is that it's very easy to generalize. If path connectedness is the idea that every map little f from S0 to x extends to a map big F from D1 to x, then we can ask, when do maps S1 to x extend to a map D2 to x? Or for that matter, when does Sn to x extend to Dn+1 to x? But we'll get there. Let's just focus for now on extending a map from a circle to a map from a disk. We call the property that every map from a circle extends to a map from the disk the property of being simply connected. It's definitely a topological invariant, just compose the required maps with your homeomorphism. Or to say it another way, being simply connected is a topological property. But we kicked the can a little bit because this is still kind of a tricky question to answer. If you want to show that two spaces are not homeomorphic by showing that one of them is simply connected and one of them is not, well, to show something is not simply connected, you have to show that there exists some map from the circle to your space that does not extend to a map from the disk to your space. And once again, that's like a non-existence kind of thing. But it is starting to be a little bit clearer that this could show that the plane and the punctured plane are not homeomorphic, because it's starting to formalize the idea of there being holes in your space. If you stick a circle around that hole, how could you fill it into a disk? Hang on, that's important, so let's say it again. Being simply connected is formalizing the idea of there being no holes. Except, there's already a problem. Remember how I said that no matter how many topological invariants we cook up, there will always be examples that we still can't distinguish? Well, suppose we believe that the punctured plane and the plane are not homeomorphic, since supposedly the plane is simply connected and the punctured plane isn't. Well, what about the twice punctured plane? That had better be non-simply connected too. So how do I tell it apart from the once punctured plane? Well, crap, now we're really stuck. The fix is that we're going to build a device that tells us more than just whether or not a space is simply connected. In a sense, it will tell us how far from simply connected your space is, by which we mean that the twice punctured plane will be more non-simply connected than the once punctured plane, because being simply connected is formalizing the idea of there being no holes, and two holes is more than one hole. The tool to build here is called a homotopy. Suppose we have two paths, P and Q, in our space X. Remember that via our old way of thinking, that just means that these are functions from the interval to our space X. Suppose further that they share the same starting and stopping points. Call those points X and Y, respectively. So here's the definition of a homotopy. Hold tight, but we'll unpack how to think about it right away. The technical definition is that a homotopy, H, is a function from I cross I to x, such that for all s in the first interval I, h of s comma 0 is p of s, and h of s comma 1 is q of s, and for all t in the second interval I, h of 0 comma t is x, and h of 1 comma t is y. Okay, so how do we think about this? So I like to think of the second interval I as a time factor, t for time. We start at time 0 with the path p, and the s-coordinate lets us be anywhere on that path. We need to finish at time 1 with the path q, and the s-coordinate still tells us position along the path. For all the times between 0 and 1, we get intermediate paths, and the s-coordinate again tells us position on that intermediate path. The fact that h of 0 comma t is x and h of 1 comma t is y tells us that for any time we get some path, And that path has to start and stop at the same x and y that the paths p and q start and stop at. Here's the picture. At time t equals 0, here's the path p, and at time t equals 1, here's the path q. And for example, at time t equals a half, we get some path like this. If there exists a homotopy between p and q, then we say that p and q are path homotopic, and we write this symbol to mean p is homotopic to q. Okay, cool beans. So that's what a homotopy is. But so what? But notice, even though we will make this very clear in the future, notice that having a homotopy between p and q is the same as filling in a circle. If p and q start and stop at the same points, then running forwards along p and backwards along q makes a circle in our space. And filling in that circle seems the same as saying that we can produce a bunch of intermediate paths between p and q down the middle. So this idea should connect to simply connectedness, and it will. Not quite in the exact same way. Instead, we'll build homotopies of loops, not just paths. But again, we'll get there. In the meantime, we're going to prove three very fundamental properties of path homotopies. Here they are. P being homotopic to Q is an equivalence relation. There's a way to quote-unquote multiply two equivalence classes of paths if they happen to start and stop in the right places. Multiplication of equivalence classes is associative. There is an equivalence class which essentially does nothing, and there are equivalence classes which essentially undo each other. I'm being hella sloppy with my language here because 1, I'm trying to get across how these things actually function, and 2, I'm not assuming that you have any algebra background right now to appreciate the precise version of what we're saying and why we would care whether or not that's true. Don't worry, we'll get there. But first, let's start with claim number 1. P being homotopic to Q is an equivalence relation. That is, it is reflexive, symmetric, and transitive. Okay, so there's 3 things to show. Being reflexive just means every path is homotopic to itself. That's easy to show. For every time value, let the homotopy be the path P itself. Being symmetric means that if P is homotopic to Q, then Q is homotopic to P. Okay, so if P is homotopic to Q, then that means there exists some homotopy from P to Q. If we run time backwards, then we get a homotopy from Q to P. Finally, being transitive means that if P is homotopic to Q and Q is homotopic to R, then P is homotopic to R. So we have a homotopy from P to Q and a homotopy from Q to R. To get a new homotopy from P to R, run the first homotopy from P to Q at double speed for the first half of time, and then run the homotopy from Q to R again at double speed for the second half of time. Great! Having an equivalence relation means that equivalence classes are well defined. We'll write brackets P for the equivalence class of a path P. On to claim number 2. If P and Q are 2 paths, and P stops at Y and Q starts at Y, then we can take the product of P and Q to be a new path which first goes along P at double walking speed and then goes along Q at double walking speed. This gives a well-defined product of equivalence classes, which is to say bracket P times bracket Q is the same as bracket P times Q. We need to show that if we have different representatives for P and Q, then their product will still give us the same equivalence class. So we need to show that if P is homotopic to P prime and Q is homotopic to Q prime, then P times Q is homotopic to P prime times Q prime. Well, we have homotopies between P and P prime and between Q and Q prime. We can use them to build a homotopy between P times Q and P prime times Q prime. All we do is, well, rather than running the time twice as fast, like we did in the last theorem, we run the walking speed twice as fast to build the homotopy between P times Q and P prime times Q prime. For the first half of time, use the homotopy between P and P prime, but walk along the paths twice as fast. And for the second half of time, use the homotopy between Q and Q prime, and again, walk along the paths twice as fast. Ta-da! Double great. We can now multiply equivalence classes together, as long as their starting and stopping points line up in the right way. And the product of the equivalence classes is just the equivalence class of the product. Finally, claim number 3. The product of classes bracket p times bracket q is associative, meaning bracket p times bracket q, then multiplied by bracket r, is the same as bracket q times bracket r, then multiplied by bracket p. Has identities up to endpoint, which means that if p starts at x and ends at y, then the constant paths at x and y, call them e sub x and e sub y respectively, satisfy bracket e sub x times bracket p equals bracket p, and bracket p times bracket e sub y equals bracket p. Has inverses, which means if p is a path that starts at x and ends at y, then the path walking backwards along p, which starts at y and ends at x, call it p bar, satisfies bracket p times bracket p bar is equal to bracket e sub x, and bracket p bar times bracket p is equal to bracket e sub y. Ha! It's a theorem fake out. This one's gonna be your homework. Do it, I demand of you. It's super easy and it's super important. Every other homework question in this series so far has been for the memes, but this one you gotta do, or you'll fail the class. This homework is worth 100% of your grade in this class. I want them on my desk by next Saturday. Hey, since you stuck around to the end, I've got a little secret bonus point thing for you. One of the cool ways to think about homotopies is by visualizing maps from squares into your space. And so it's worthwhile to unpack how you might do that, and also prove some of the theorems that we proved today just by drawing squares for your domains. So good luck, and I'll see you next week. Do your homework.